So this is the beginning of our final exam review guide, going over it. Some of these we'll do out, and some of them I'll just voice over, so we'll save us some writing some time. But in terms of the difference between the ground state and an excited state for an electron, if we have a simple Bohr model with our nucleus, and we'll just go very simply with two shells, and say this is a hydrogen atom with just one electron. This one electron, when it's in the ground state, is going to occupy the lowest possible energy level. That's the energy level closest to the nucleus. If some energy, in the case of when we did the flame lab, the heat from the flame comes in, that energy, when it strikes an electron, if it's just enough energy, can cause that electron to jump up to the next highest energy level, or even skip a few energy levels. So that's what happens when the atom becomes excited, or the electron becomes that excited. So there's space in lower energy levels that are not taken, and that electron now occupies a higher energy level, so it's jumped up. So this would be an example of a ground state over here, and this is an excited state for this one. In terms of our definitions there with the Aufbau principle, this basically states that electrons are going to go into the lowest available energy level, and that chart that we have with our numbers and arrows that we end up with our electron configuration is using this Aufbau principle. So the lowest place for an electron in terms of energy to go is on the 1s sublevel, and then we'll fill that, and then go to 2s, and then 2p, and then so on and so forth. So that's, we get that order from that Aufbau chart, which I'm not going to draw the whole thing here, but I'll just draw part of it. S, 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 and P, bunch of P's there. So we're just follow these arrows with the first one's going to 1s, then 2s, then 2p, then 3s, and 3p, and 4s, and so on and so forth. So that's our Aufbau principle. Electrons fill the lowest available energy levels for atoms. In terms of the Pauli exclusion principle, basically this states that at most in any orbital, if you remember orbitals, that's when we can draw little boxes to represent our sublevels. Each one of these boxes is an orbital, so this represents a p sublevel. There's three boxes here. We can fit 2 electrons in that. The Pauli exclusion principle says that if we have 4 to fit in a p, we would put 1 in each of these, and then come back and then fill up, double them up. And it means they also have to have opposite spins. That's what those arrows are referring to. And for clarification here, I actually combined Pauli exclusion with Hund's rule. Hund's rule is every sublevel, every orbital has to have at least 1 electron in there before we double up. So Hund's rule prevents things like this. That's no good. We want this. Same number of arrows, but we want to have 1 arrow in each box before we double them up. Whereas the Pauli exclusion basically says that no more than 2 electrons per orbital. All right, scrolling down here, Heisenberg uncertainty principle. This just states that for really small things like electrons, we can't know their location and their velocity at the same time. So we can either know where they are or we know what they're doing, but not both. And so that means that we can't ever pin down exactly where an electron is. So this leads us to our probability, our cloud model of the atom, where the electrons occupy a space of probability. So it kind of shifts our model of the atom from having those concentric rings or shells to having areas of kind of likelihood of finding electrons. As far as the next part here, these are pretty straightforward. What are the following? What are the designations for the 4 sublevels? Well, we've got our S, our P, our D, and our F sublevels. And how many orbitals does each one have? So if we were to draw the orbital diagram, how many boxes would each one of these have? The S would have 1, the P would have 3, and then we would have 5, and then we would have 7 for an F. So if you notice, These are the first four odd numbers. So that's a way to remember it. 1, 3, 5, 7. So we look at the next part here. We're looking at the full electron configurations for these. I've gone ahead and drawn an F-bow chart. You'll get one for the exam, and it's not hand-drawn, so it's easier to see what's going on here. So the idea here is we want to find out where all the electrons for each of these elements are going. So nitrogen, its atomic number is 7. So it has 7 electrons. We're going to put the first electrons in our 1s, and the s sublevel we said it can fit 2 electrons. Come to the end of this row, we're going to go to the next row. The first thing we encounter is 2s. And again, regardless of it's a 1s, 2s, 3s, 4s, any s can fit 2 electrons. So that means we've got 4 of our 7 electrons accounted for. So after our 2s is filled up, we go to 2p. P can hold up to 6, but we really only need room for 3. So we're going to put 3 electrons in there. So that's what this would look like for nitrogen. This is our complete electron configuration for nitrogen. Strontium, on the other hand, has an atomic number of 38, so we've got to account for 38 electrons. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So I'm just continuing down here. Now we're going to go to 3d, 10. But now then I like to take a stop and count up to see we're close. So we got 2, 4, 10, 12, 18, 20. We're at 30, so we need 8 more to go. So we're going to put 6 in our 4p. Oops. And then we can fit 2 in our 5s, and that brings us up to 38. Now with the next one, instead of writing all these things out, especially for bigger elements like gold or uranium or iridium or any of those, it becomes a bit more labor intensive to draw all these things out. So since it's only the valence electrons, the outer electrons, that have anything to do with the chemistry of these elements, for the most part, we can ignore all the electrons in the inner parts of the shells. And the way we do that is with our noble gas configuration. So looking at the periodic table, you find calcium. You go up one row and then all the way to the right and find what noble gas is there. So with calcium, if you looked at your periodic table, the noble gas that we're going to jump off from is argon. Well, calcium has 20 electrons. Argon has 18 electrons, and these are just the atomic numbers of those 2 elements. So that means argon, or calcium, is argon plus 2 more electrons. The question is, where do we find, or where do we put those 2 extra electrons? And so we're going to use this here, and we're going to use the periodic table to figure out where argon would be. Well, all these noble gases are all the way to the right of the periodic table, which means they're, with the exception of helium, are in the p block. Argon happens to be 3 elements down in the p block, so it's in the 3rd row of the p block. So argon's electron configuration would include everything up through 3p. So after we filled 3p, where would we go? Well, 4s. So we're going to continue with 4s. Now, how many electrons can fit in the s sublevel? That's right, 2. That's all we need. So this is the abbreviated notation for calcium. Gold, a bit more, no more difficult, but it's a much bigger element. Gold has 79 electrons. And the noble gas, if we find gold, it's kind of down there in our valley of mystery, or the transition metals, the D block. We're going to go up a row and then go all the way to the right, and we find xenon. Xenon, again, is in our P block, all the way to the right. And xenon is, let's see, helium, neon, argon, krypton. Xenon is 5 down. So 1, 2, 3, 4, 5. So that means xenon includes everything up through 5p. Well, xenon, let's take a look. We've got 54 electrons in xenon. To go from 54 to 79, we need to account for 25 more electrons. So gold is really xenon plus 25 electrons. So where would we pick up? Well, where 5p left off. So 2 of those 25 electrons we need to find a home for go into our 6s. After 6s, we go to 4f, and f can fit 14 electrons. So that brings us up to 16. We need 9 more electrons. After 4f, we go to 5d, and d can fit up to 10, but we only have 9, so that's where we would leave off. So instead of writing out 1s2, 2s2, 2p6, all the way up through 5d9, we can just write our abbreviated notation here, and that's all we got here. In terms of our orbital notation, this is where we draw our boxes or circles, some people like to do, or dashes. to represent those orbitals. And also for phosphorus, if we look at the periodic table, has 15 electrons. So we're going to put our first electrons in the 1s. We're following our off-bow chart again here. And I usually like to use boxes, but if you use circles or lines, that's fine too. We label this as 1s, and we can fit 2 electrons in there. It's an up and a down arrow. I like using these half arrows just because they're quicker. So as opposed to going, we can just do this as opposed to taking our pencil off the line, the paper. It makes it a little bit more of a pain. So ignore all that up there. So 1s, that's 2 of our 15 electrons. We go to 2s, and it looks just like a 1s. We're going to put our 2 electrons in there. After 2s gets filled, we go to 2p, and this is a bank of 3 boxes. And let's see, we need, we can totally fill this. So this would give us a total of 10. We need 15 electrons. So there we go. There's our 10 electrons. We need 5 more. So after 2p, we go to 3s. A 3s is just a single box with 2 electrons in there. So that brings us up to 12. We need 3 more. So this is going to bring us to our 3p. 3s, then 3p. And instead of putting an arrow here and another arrow there and an arrow here, leaving this one half empty and this one completely empty, the Hund's rule says we've got to put an electron in every one of them before we double them up. So we should have 15 arrows because we have 15 as our atomic number, or 15 electrons for phosphorus. Alright. So let's take a look at these contributions to each of these people here. So Lavoisier, he was French. He really is like the father of modern chemistry. He made a list of the known elements at the time. They weren't really in any particular order, but he met his end to the guillotine because he was a tax collector for the French royalties during the French Revolution. So it was a big loss to science with his loss. So basically made a list of the known elements, really kind of brought chemistry out of the ages of the alchemists to more of like, took a scientific approach to things. John Newlands, he was known for his rule of octaves. He noticed that certain trends tend to repeat with every 8 elements. So because he called this the law of octaves, he was kind of made fun of for it. People thought, well, it's music and chemistry have nothing to relate to each other, so you're kind of nutty. So, but it turns out that the more we knew, the more he was correct. Now, just like Lavoisier was the father of modern chemistry, Mendeleev is considered the father of the modern periodic table. So what Mendeleev did was he took all the known elements at the time and arranged them by mass. Now, this is before we ever knew about protons, neutrons, or electrons, so there was no such thing as an atomic number. But they knew relative to one another what the masses of the elements were. They're basically related at all to the lightest element, hydrogen. So when he did this, he noticed that there were some astonishing patterns or trends. And so much so that he noticed that there were some gaps for elements that had yet to be discovered. To me, that's pretty impressive. This guy kind of seemed to be a little bit cocky in terms of, there were some holes in his periodic table, and he felt that they should be corrected. And those holes, he went as so far to predict properties of the elements that have been yet to be discovered. So people, kind of thought he was a little kooky in that regard. I always think of it as like a baseball player calling their shot when they stepped up to the plate. If they point to the left field wall, say it's going to hit a home run, that's pretty gutsy. But he delivered because within his lifetime, at least 2 of the 3 blanks that he left on the periodic table had been filled, and the properties turned out to be very close to ones that he predicted. Moseley, he kind of piggybacked off of Mendeleev. He took advantage of the fact that he discovered a way to determine the number of protons using X-rays and the relationship to the energy given off by the atoms. So he found that there were a couple inconsistencies with Mendeleev, but those consistencies or inconsistencies were fixed when we arranged the periodic table by increasing atomic number. So if we increase the atomic number, we're making the elements larger by 1 proton, and this is essentially the way we see the periodic table today. So we'll stop here for part 1.